Hi everyone, and welcome to this first SceneView video tutorial, even if it won't be really a technical tutorial, but a bit more an introduction, so we will guide you through the way to realize your project in 3D as an Android developer, native Android developer, and do stuff like this, which is step in the 3D world, simple model viewer with a skybox around, which will display everything around the 3D world. I will explain you a little bit more precisely later. So let's get started. Here we are in Android Studio. You may know. First thing to do, like always, is to grab the dependency area in the SceneView repository, which is not the same as a SceneForm, which is not deprecated. We are still working on it, but we prefer bring new features to SceneView, which is the Kotlin version. Not the Kotlin version of SceneForm, since it's working a little bit differently, just a little bit, you'll see. But we renew the core part of SceneForm, and especially the mathematical part, which is now made of Kotlin Math library made by Romangi, which lets you manage 3D position, rotation, and everything around matrices, which you will discover during time, during evolving in the 3D world. So let's get started. So grab the dependency. Just quick note: there is two different dependencies. One for 3D only and one including higher core, dependent on SceneView, and you can also just grab the SceneView one in order to limit the size and calls to possible error functions. So if your project is 3D only, may choose to only use this one. Okay, so back to Android Studio. It's within Maven Central, so you don't have to change anything around the repository you're using. So here we see the dependency SceneView. Use different implementation in case of debug release. Here we choose to use different one. You can add this this part, which will not compress filament files, filament compiled files, and go to our manifest. In particular, in here, it's standard Android manifest. In our case, we use an activity, which is not just a container of the fragment. You can have multiple fragments without any issue, and with possibly multiple scene view inside. Go to the layout. As you can see, you can include the scene view directly, like any standard Android view. Compose is coming next. We have people working on it, but it will be soon available. So standard Android view, we can here define transparent background. They change the way the 3D surface view is rendered. It's a bit particular in case of 3D. It's not just like a standard view, but you just have to know that it's handled by SceneView. So next, nothing special in here. You can retry your scene view just like any other view. We have included the loading view just right here, which is not visible at start. So here is the view and full screen, but it will be possible to define any value you want here, and you can also have multiple scene view just like this, and place it anywhere you want in your layout. But you can manage multiple scene view at the same time, which is not the case for now with air scene view, but this is another subject. Camera position is from where you are looking your object. Camera is here pointing at an object which is within its near plane and far plane, and inside is FOV field of view. Okay, that's just a little parent. You can see that node in case of SceneView, because Air SceneView have a lot of more nodes. But in your case, in 3D only, it can be light, so you can adjust whatever light you want, like directional or like sun, to provide some cool rendering effects. Can also be a loading node, which is simply a view, a progress view, progress bar view, displaying in 3D world, so it can be useful in case of model loading or other things loading. You can manage it just by placing a loading node while the node is not currently loaded. Model node, but the use node, it's under renderable. Renderable is loaded by the loading model functions. Come back to Android Studio. So a model node is node with a GLB source file, which is a format, binary format of GLTF file. We prefer using GLB because in the mobile app usage, it's more appropriate and easier to handle than GLTF format export, which is made of texture file, external texture file. It can be useful in case you want to change the texture inside your subfolder, but you can also do it programmatically. So GLB might be a better file format in our point of view. So you load your model from a GLB file, which can come from multiple sources. Sources. First, a relative asset file location defined in the subfolder of your assets folder. In this case, in this sample, we don't have one because we load it from a server using HTTPS, but it could be located right here. Your model can be located right here. and you just have to provide the asset really relative URL like this. You can also use a resource which maybe in the raise raw folder, but we don't really advise you doing this because first you will lose extension part within your resource. In many cases you will have to handle multiple files with maybe the same name but not the same extension. As you can see here, you may encounter some different file types depending on your usage case. In most cases limited to importing a GLB file, so model folder will be enough, but you can see that it will be complicated to manage maybe too long wording for raw value because you have to distinguish each kind of source file. You can also use a local file, make sure to have access to it, and finally you can also load it using HTTP or HTTPS URL. Yeah, one quick more precision, if you are using a raw resource, make sure to use this call. So the load model function also have an auto-animate parameter in case your GLB is animated, sorry. You can go further with animation inside your model using model animation part of SceneView, which is not Kotlin yet, but soon it will be. Auto-animate will under the default playing and loop for you. Auto-squall will squall your model into your unit cube. We won't talk about it more in here, but unit cube is in case of air we could use a meter unit, but it's a 1 by 1 by 1 cube that will let you fill your model into it. Let me show you. It will scroll your model to fit inside, but keeping the same ratio, the same square ratio. So your model keeps its rendering, but fit into this cube. Why fitting inside the unit cube? We want to fit it inside here because when we are rendering, we want the model be at the same size of what is looking inside is a coordinate system. It will correspond to 1 unit in your coordinate system, so you can easily make it fit your actual screen rendering. Screen scene view. Center origin, just like if you have worked a little bit with Blender, origin is a coordinate point. If we want to have an anchor at bottom position of the cube, we can change it with this parameter. Model inside your node will be positioned at this location. Let me explain a little bit more with sample value. The center origin is 0, 0, 0. Your cube will be placed like this. This is a 0 center origin, like here, and if we want to anchor it at the center horizontal bottom, we will define that the center origin point is a y -1, and other value will be 0 to keep them at the center of your model. Coming back to the cube, In this case, the cube will be placed like this, so that the positioning part, when loading a model, you have an on error. You may not encounter any issue loading it. You can encounter an HTTP error in here coming from the HTTP lib library. Because yes, here we under quarantine context in which the model is loaded. We are in the main context by default because every call to filament modification have to be done in the first calling thread. So in your case, it's a main thread. So it's a main quarantine context. Sorry. Which have to call it, but you can use it. You can also use it independently to load your model and then call the set model function. You can load your model within your own coroutine scope, or you can load it asyncly in case of Java usage, or in case you're loading outside of any coroutine scope your model. So this will handle the lifecycle states for you. So in this case, it will be launched when the lifecycle is in the created state. And we'll cancel it. Most interesting part, not most interesting, because a lot of things are behind those great lifecycle functions. But it will cancel the loading process in case of your fragment activity is destroyed before the end of loading. In case you don't provide a coroutine scope in here, we will use the SceneView one, which is the fragment or activity one, depending on where you place your SceneView. This little library gives extension function to view, to retrieve directly the life cycle of the attached parent hierarchy view tree. So back here, so in case you don't provide any coroutine scope, your model loading will be done at the model node attached to the SceneView. So when you call SceneView.addChild model node, the life cycle is retrieved from the SceneView you provided, so the parent of your node, because SceneView is also a node. If the SceneView is already attached, the call is done directly. If it's not the case, we are checking for the attach event on the node. So back here, so this is maybe the worst case you may use not providing a coroutine scope, because your model will be loaded at the time it is attached. It will be a better choice to just provide the life cycle in order to handle it as soon as possible. This can be very useful in the other hand because you may want your model to only load when it is attached to the view. For example, in case of the not selector, not selection recently I did. In case of the selector node, you may prefer to load it only when it's needed. in order to limit actual memory consumption. But in most cases, you may call it just like in the sample, and the fragment is created, is at least at the created state. Let me just disable so you can have a quick view of a more basic, let's say, a more basic simple usage. Here we don't enable the environment, and let's start the emulator. By the way, you can go here if you want some test assets. Always make sure to test your model before doing anything on the app development part. You can find many GLTF viewer online, including the filament one. I disabled every camera change and the loaded environment, so you can see very more simple, simpler sample. 5 lines of code, you can display your model. So yes, in this sample, I also removed the environment to show you that the actual background within your layout is displayed behind the SceneView, and that it's visible since the SceneView background is transparent. Let's try some different usage for the auto scroll param. As you can see here, our model is quite big, and we cannot see every part of it. So let's enable the auto scroll here, and let's see. The loading part is a little bit long because we didn't manage any HTTP cache for now. So here you can see that in case of photo squatting, your model is just scroll to its right size to fit inside the SceneView. After that, we can define the center origin. Center origin is null by default to keep the original model center point origin as defined in the exported GLB. So let's change it to see what's happening. Let's say that we want it to be at -1 on the x-axis and +1 in the y-axis. So let's see the result. You will see it should be anchored right here, yeah. Because we defined the origin point at -1, so x0 is here, and we define it at -1, so at the left part, and to put the origin at the top, so the node origin is here, just at the top position of the model. Okay, that's for the positioning model part within a node. A node also have a position Z position is not 0 because this position in the coordinate system is the position of the camera. So coming back here, you can have more environment view. This is, by the way, this is different lighting you can have inside your scene with light direction. So coming back to our position, yeah, it's the case here, as you can see in Blender. If you define your model node at the 0, position, it will be like, sorry, it's quite difficult with the zoom. It will be placed just like this. So you won't be able to see most part of your model. So by default, coming back here, the model position, Z position, placed at 4 units in front of the camera. So here you can consider that there is 4 units and that the camera is yourself and you are and the model is at 4 units from you. To be more concrete, in a higher case, in a higher case, the unit you defined, the Z unit you defined here, so the negative value here will correspond to the number of meters you are from the model object. So the phone is from the model object. Node position is by default -4 units far away from you. We are not talking here about rotation, but the default rotation is 0, 0, 0 also. We keep it just like it is defined at you can see it because it's a sphere, but we keep it as defined by default as here, so the rotation will be the same as defined as the export time of your model. But you can change it also, obviously. You can also change the squall, which is also the same, so you might type the same export squall as you will have it by default. Coming back here, so here we will define that we will not change the Z position. Yeah, one quick good thing about Kotlin map is that you can change the position, rotation, and squall each acts independently. In this case, you will define the x, y, z position at 0. Back here, let's do some rotation on the node. Rotation equal rotation. Just as easy as this. You can use different rotation types. Quaternium is part of the game, mostly useful in case of animation, in case of smooth transform, because here you can see that you are applying the new node transform directly, but you can also call the smooth function. Won't go further into Quaternium, even it's a very, very interesting subject. Maybe I will talk about it on another tutorial, but let's just stay in your rotation case. So here you can define each axis rotation. So here it's working. You can see that the rotation has been made within the y-axis. One thing very important that you have to keep in mind is that we have different camera system between air and standard 3D usage. In standard 3D usage, manipulator, which is not implemented completely yet inside SceneView, but people are also working on it. The manipulator will, so the gesture you will have on the screen will be made on the camera object, not on the object itself. So when you are doing gesture in your screen, this virtual camera will move, but not the object. At the opposite to air, in which case the phone and the camera here is moving, so you cannot interact with your screen because because your physical camera is already linked to this camera position. So this one and this one will be kept constantly together. So you won't be able to change the camera position. So in this case, you are moving the object, but not in 3D normal usage. So coming back in our sample, let's try to move the camera a little bit. Okay, so we are going to change the camera position, default camera position, from 0, 0, 0 to this position and this rotation. By default, so the movement will start from here. We will see after this how to define an environment, but let's keep it just like it right now with the transparent background, and let's move the position now and rotation. So the smooth function made some layer function calls, which are mathematical function to make your move linearly interpolated when moving. I won't go further in details, but just to let you know, we use this the SLERP spherical linear interpolation for rotation in order to keep them smooth and to keep rotation behavior. Won't go in details in here also, but in case of Euler rotation, you can have some trouble doing smooth things around it. We'll see that the camera position is different at the starting time, and maybe the model is not visible at the start time because we have an angle not looking at it. You can use some look-at functions directly integrated in the Kotlin map to make sure to always keep a look at the model node, but for simplified reason, here we defined it statically. So you may have noticed that the animation is running great. We can choose a smooth speed to increase or decrease the time it will make to go from the starting value to the smooth end value. That's it. And now let's see how it's rendered with an environment. So what is an environment? Coming back here, an environment is made of a skybox. The skybox, it's what you see in here. In Blender, you can change it just like here, just like it. It's what around your scene. It's defined as a cube. Yes, I made it right here. It's defined as a cube, which makes you feel that you're inside this cube, but it's multiple images on each face that make you feel upper and down integrated, that make you feel that you're inside this world. So in here you can see that your actual camera is inside this world. So when it rotates, so when you move here, you can see that you will have a different look. So that's how you make a skybox. So that's what you will see on your screen, actually, because this is a camera view. So you see that while moving the camera, the environment keep stable and keep behind everything. What's happening there? Okay. This environment also generates what you see in here. What you see here are reflection, lightning, reflection on the texture. In our case, we have a very reflective texture in here, a material in here, since it's defined, it's full metal and its roughness is more about zero, so the material look more like a metal ball, and I can go up also reduce even more. So here you can see that reflection are coming, so the street actual reflection are coming on the metal ball reflection, and also the lighting point here, and many lot of things that are coming from this environment. So how do we handle it within SceneView? Within mostly filament, because SceneView is made with filament. We handle it with two file formats. First one is HDR, HDR file. Let me find it for you. You can find some great sites, websites around it, like Polyhaven, in which you can choose whichever environment you like. Which is just a flat image, but after that, filament will take care of dividing each part of the flattened image to make it fit into the skybox and the generated indirect light cube. So let's take it, for example. We can download the HDR. Make sure to keep the output format. Yeah, it might look very impressive here to go 16K, but you have to remember that this will be divided within multiple phases. So 2K is quite a good compromise for mobile usage. In this case, so we define the environment coming back from this loader, from the file we just seen before. In this case, every calculation to make your reflection here on the balls will be calculated during the runtime. So it's not the better choice you might go for. Instead, you will better use a KTX file. KTX files are compiled files made by the filament engine, and which are also pre-compiled, and which will do the environment lighting and cube map generation, so the skybox generation at the building time, not at the runtime. To use it, we recently included KTX generator. So this groovy file will check for your root assets folder files, and in our case, our HDR file, or a material file, but that's another subject, which will be compiled to filament. But in our case, we want to convert the HDR to a compiled KTX file. Do I have a sample of KTX file in here? Here is the result. So here is the result. Need direct light. IBL means image-based light. So lights are coming from source image, the HDR one, and the skybox, which is what you have around here. So it will be a better choice to use KTX directly here and to use it just like it, SceneView.environment. equals KTX loader dot load environment. You can see that you can also load it async, but since we are in the quarantine scope, we can call the suspend one, and here you will give the IBL file location and the KTX and the skybox KTX file location generated from your default HDR file. Like always, everything can be loaded from asset folder, res folder, or from HTTP file, but that will be a better choice instead of using HDR in here, even if it's easier. But for production reason, you would prefer to use KTX. So here we define our environment. By the way, environment HDR file can be opened with GIMP. I won't launch it right now, but you can view your image, HDR image, and modify it within GIMP. So let's see the results with our current HDR sample. It's incremented, clean up. Okay, you can already see Skybox during the loading time, and here you see the results. And you can also see here that the model has completely changed comparing to before, because we now have something to show in this reflection part, at the opposite of before, in which case we didn't have anything around, so we cannot reflect anything. So here you can see that the actual HDR is reflected by filament, and that also every other material types are reflecting or not part of the actual studio. So that's it for not quick. Sorry, I'm too passionate about this to make it short. But very quick demo of what you can basically do with, in case of model viewer, within SceneView on 3D only. But you can do much more things thanks to filament engine and thanks to the fact that we try to give you access to every filament function and to bring them to a simple usage SceneView and to bring some feature specific to Android lifecycle, aware components, and other stuff that you will have within an Android app. But you may not encounter in other context, and filament is more multi-platform, so not dedicated to one precisely, even if a lot of samples and utils are made for Android within filament. We enjoy to make you not being afraid of using it, but by bringing you some Kotlin function to help you starting with it. You can have a look for sure at the SceneView website from some, first of all, our partners, some feature which are mostly here feature included in filament, and features coming from AirCore. You can use a list of all things around AR and 3D on the app page, some Great samples are here. You have access to the API of each area or SceneView only part. And you can contribute to our community made of people working mostly during nights and weekends. This framework and which also need some help financially in order to buy things like the actual mic I'm using, or things to be more productive in the framework building, such as some memory that I should need when I see the current lag when running the emulator, OBS, and some other stuff. Quick little details. Blender at same time. So contribution mostly for that and to bring back some money also to people who would like to bring some new article. If you are interested in bringing articles made around the article or video tutorial made around SceneView, we will be happy. You can go there and have a look at actual financial part. So yeah, here it is. You can sponsor us in here. Our goal is not to become rich in here, just to share our passion around the area subject and to make it available to everyone. But we might need some money to continue doing this. You can also come to our Discord channel, in which we will be happy to answer every question you have. Make sure to go to the help section if you need some help, but also be sure not to use it as an issue tracker. Better choice is to create an issue directly on the SceneView repository. Right here you can pull requests. We are completely open to any pull request, and the actual team will also have the pleasure to answer your questions and to help you create your pull request. You can also go to the discussion section, and that's it for the first presentation of SceneView. Let me come back here. Thanks for watching, and hope you will enjoy our current work on the 3D part inside Android native application.